So in this video, I'll be introducing our next chapter, waves. It's a part of waves and vibration. So in this chapter, we're gonna first, discuss the waves, types of waves, and then wave equations. We're gonna solve some problems on wave equation, wave speed, and finally briefly introduce the sound waves. And so first of all. What is a wave? A wave is as you know, a disturbance in the medium that travels through the space and time, usually by transfer of energy, right? Just for an example, if you throw a stone on a still water or pond, it creates the disturbance in the water molecules, and the disturbance just travels outward as a wave. That's called wave. And basically, there are three basic types of waves: mechanical waves, electromagnetic waves, which are light, and radio waves are example of electromagnetic waves, and matter waves are the subatomic particles like electrons, protons. They can behave as a wave, and sometimes they're particles. So these are called matter waves. But in this chapter, we'll be basically dealing with the mechanical waves because we're doing the mechanics. Well, the simplest example is to create a wave is just by using a string, just clamp one end of the string to the wall, and the other one, if you just shake it up and down, you're creating a wave. And mechanical waves are of two types: transverse wave and longitudinal wave. So transverse waves are if the particles of the medium vibrate, oscillate, perpendicular to the direction of the propagation of the wave, something like that. It's called transverse wave. So the particles are connected to each other, by some intermolecular force, some weak intermolecular force, and that can be modeled by a spring-like force. So all these particles are oscillating in phase. They have a slight phase difference from each other, and this is called transverse wave. Example is this, and the waves on a string is also an example of transverse wave. So particles are again are connected by elastic intermolecular type force, spring-like force. And what is longitudinal wave? Longitudinal wave is, if the particles of the medium vibrate in parallel with the direction of the propagation of the wave, it's called longitudinal wave. And the best example is sound waves, because when this speaker cone vibrates, it generates the wave, the disturbance in the air molecules vibrate, something like that. If you could see, and this is an example of longitudinal wave. So here's the important point to note. So waves transfer energy, okay, not the particles. And each particle in the medium is simple harmonic oscillator, and we know the behavior of simple harmonic oscillator. We know the equation, right? And wave speed depends only on the medium, the type of medium, the material medium it uses. Properties such as density and elastic nature of the medium, stuff like that. Wave speed do not depend on the frequency of the source and the transverse speed of the particles of the medium. So these are the most important point to note in waves. So again, so here's an example of longitudinal wave, right? So particles simply oscillate, simple harmonically, actually, and it transmits energy, right? Actually, the particles of the medium are not transferring from one point to other point. It's just vibrating. So something like that, in this animation, it clearly shows the particle in the medium. It's just simple harmonic oscillator, right? It's just oscillating to and fro. And this is another example of water wave. And water wave has both components, actually, transverse and longitudinal components. So water wave is actually a combination of both. So here's the other wave. People do it for fun during the sport games. I'm gonna quickly show you this. So here's an example of how a wave is generated. So this is a human wave people do for fun. So basically, the generation of wave is same actually. So people in the stadium basically just sit up and down, right? In a phase, just sit up and then again next time again up, right? But basically, people are not moving from one point to other. They are just something oscillating, and that actually generates the wave, human wave, as you can see, right? This is the basic idea of generation any wave. The sound wave, the waves in a string also generate same thing. So this people you can just consider a simple harmonic oscillator. So they can generate a wave pattern. So here's we can uh, you know again you can use the mathematics, mathematical equations to represent a traveling wave, just like a simple harmonic oscillation can be represented by a equation, just like that. A traveling wave, any wave traveling through the medium, can be represented by mathematical equations. So let's get the physical idea. So first of all, wave actually wave function, a mathematical function of wave. Wave should be a function of both time and space and time. All right. So this is a three-dimensional picture. Say so. This is a wave pattern. Say at t0, 0 seconds. So in t is 1 second, this pattern will change, right? Because it skips since the wave is transmitted, transmitting from one point to other point. This is at t 2 seconds, 3 seconds, 4 seconds, 5 seconds. And if you just run this movie, and you'll get a traveling wave. So this is the physical description of a wave in three dimension. So that's why wave should be a function of both, function of both space and time, distance and time. So here's another example. So this is a snapshot of the wave pattern, graphical wave pattern at t 0 second, quarter of the time period. It will be something like that. The peak has shifted a little bit, and another quarter second it will be here, and something like that. And if you combine everything together in a movie, and you get the traveling wave. So here's the equation we'll be using to represent the traveling wave. So it's y is the displacement, for a given wave. It's a function of both distance and time, the x distance and time. It's not just a function of t, unlike simple harmonic oscillator. Is a some cos or sine kx plus and minus omega t plus some initial phase. So a is the amplitude, k is 2 pi over the wavelength. Lambda is called wavelength. Is the wave This k is called wave number. Omega is 2 pi f is the angular frequency, and phi is the phase angle. So what is a wavelength? So lambda, this is the wavelength. This peak to peak distance here, this peak to peak distance, right? It's called wavelength. So again, understanding a little bit more about the wave function, So you're given this wave function for a given traveling wave. So now if you just take a snapshot of the pattern at t 0 second, right? So this would be your snapshot at t 0 seconds, right? So you just make this t0 in this equation, and then you will get this wave function, and this is just the y versus x. Remember, this axis is important. This is a y versus x at given time. So just take the snapshot at t0. So it's a wave pattern. Now you see the second part. So now you can do and you can check the wave pattern, the oscillating wave particles, the waves at x0. So just pick some distance position, say let's say x is equal to 0 for simplicity, and then it just becomes a simple harmonic oscillator. For a given position, x is 0, x is 1 meter. If you look at the particle, it's just a simple harmonic oscillation. So this is just y versus t. It's just a simple harmonic oscillation. So again, mathematical equations for traveling wave. If a wave is traveling forward in positive x direction, you use this equation. So there's a, remember, plus and minus. Then minus is used for a traveling wave traveling in the positive direction. Okay, not negative direction, positive direction. And if a wave is traveling to the negative x direction, you know, you use positive sign here. Okay, that's opposite. And here's the properties of wave, just like simple harmonic oscillation. So A is the amplitude, and what is amplitude? Amplitude is the maximum displacement. Okay, and lambda is the wavelength, which is just the peak to peak, up trough to trough distance. Big T is time period, is the period for the oscillating particle, and inverse of T is the frequency. And what's the transfer speed in the wave? So remember again, like I mentioned, actually, each particle of the medium is just a simple harmonic oscillator. And then you can just model by a simple harmonic oscillation. So how do you find the transfer speed of the particle, not the wave, the particles, the transfer speed of the particle, each particle. So just take the wave function for the given wave and take the time derivative of this, and that's going to get you the transfer speed of this particle's transfer speed. So now next is, before we do some problems, we're going to do some wave speed of wave. So again, the wave is both a function of distance or space and time, right? So this is the snapshot of the wave pattern at t0. This is the snapshot of the at quarter of a period. This is a snapshot at half the time period and three-fourths of the time period, and finally time full period. So as the particle oscillate with full period, for a full period, look at this peak. The peak has shifted by one lambda, one wavelength, right? As the particle oscillate completely when full wave, full cycle, as a transverse motion, this peak of the wave has transferred by actually has traveled by exactly lambda distance. So then how do you find the speed of the wave? So then speed of wave is just distance travel divided by total time. So total distance travel is lambda, and what's the total time? T, the period, and 1 over period is the frequency. So this is a very important relation actually. The speed of any wave, not the this is not the transverse speed of the particle of the medium. This is the wave speed, the pattern, the wave pattern speed. Right? The speed of the wave pattern is given by lambda times frequency. The wavelength times frequency is the wave speed. So this is a very important relation that we're going to need for numerical calculations. So another thing you have to know is, so what factors, control the speed of wave? So for example, we speed of wave in a string, which we are going to use in the next chapter. The speed of wave depends on the tension and mass per unit length of the string, which is basically the linear mass density. So we're not going to derive that. I'm just going to show you the formula. This is the speed of the wave on a given string. The transverse wave speed is the tension force divided by this mass density, linear mass density, mu. So this lecture is on superposition of waves. So especially we'll be talking about the standing waves, the generation of standing waves, and finally interference of sound waves. So we'll be talking about so what happens when you combine two waves, traveling in same direction, traveling in opposite direction, what would be the resultant wave? So some stuff like that. So first thing is, what is superposition principle? So superposition principle in mathematics simply says, the resultant, if you combine two wave functions, two waves, uh, you know, uh, the resultant wave function is just the linear combination of the individual wave functions, in the individual displacements. So this equation here is simply, the superposition principle. Okay. So here in this example, there are two wave pulses, Gaussian, wave pulses traveling to each other, and they combine. So let's see what happened at this 10 seconds. So you can clearly see, right? The resultant wave has a displacement, which is the linear combination, which is the algebraic sum of the individual displacement. That's simply the That's simply called superposition principle in mathematics. So here's another example. And also make sure to check out my separate video on superposition and standing wave animation video. So since we are combining waves, and wave functions are the mathematical wave functions are have sine and cosines. So these are the trigonometric relations we'll be using. So sine A plus sine B is this, sine A minus B, sine A plus cos B gives you this. So we'll be using these trigonometric relations to find out the resultant. So here first, so this superposition or combination of waves is also called interference of waves. That's the language in waves. Interference means just the superposition. So here we're combining two waves traveling in same direction, two identical waves traveling in same direction, right? The only difference is the phase difference. So this is the first wave. This is the first one, right? So A cos some kx minus omega t, right? Having zero phase difference, initial phase. And the second wave, the only difference is the phase, initial phase. So something like that. If this is the first wave, if this is the first wave, why one second wave is this. They have same amplitude, same frequency, same wavelength and everything. The only difference is the initial phase. Okay. So what would be the resultant wave, mathematically, if you combine these two? Then since you're dealing with cos, right, and resultant according to the superposition principle, the total displacement of the resulting wave will be y1 plus y2, and you are just adding these two cos functions, and then using these trigonometric relations that I showed you, you just try to simplify that, and that's what you get. So this is the resultant wave function. So if you combine two waves traveling in same direction, having some phase difference between them, this should be the this should be the resultant wave. And you can clearly see you have some constant. This whole thing is a constant because initial phase is constant. Times some again wave function. So this is similar to the traveling wave, right? This is another traveling wave having different amplitude. This is the new amplitude. It's 2a cos. So the amplitude depends on the initial phase, so which we will talk about next. So first, constructive interference. So what happens if the phase difference, the initial phase difference between these two waves is zero? Zero means like this: zero or 2 pi or 4 pi or 6 pi. So in that case, if you put here, if phi is zero, phi is 2 pi, for 4 pi, you get the new amplitude as twice a. The new resultant wave will have double the amplitude, and this kind of interference is called constructive interference. So you get constructive interference of waves when two waves meet in phase. This is called in phase, same phase, right? And this is another explanation of constructive interference. When two waves have a phase difference of 0 or 2 pi or 4 pi, this, even number integer of pi, like this, then they meet constructively, right? There will be a constructive interference or something like that, peak to peak, trough to trough, right? And if the second wave is shifted by 2 pi, again they will meet, peak to peak, trough to trough in phase, again in phase. So then you will have a resultant wave having double the amplitude, right? So next is destructive interference. Now, if two waves meet like this is called out of phase, right? If two waves have an initial phase difference of pi or 3 pi or 5 pi and so on, the odd half multiple of pi, then from this equation, the new amplitude will be 0, because if you put pi over 2 is cos 90 is 0 and so on. So the resultant wave will have 0 amplitude. So they will just cancel out. The two waves will cancel out if they meet like this, if they meet out of phase like this, with this phase differences. And this is called destructive interference because they kind of destroy each other. And this is how you explain. If the phase difference between first and second wave differ by pi, which is 180 degree, they meet trough with peak with trough, something like that. So the resultant wave will have 0 amplitude. Same thing, if the two waves phase differences differ by 3 pi or 5 pi and so on, they will meet destructively. So here's some more examples. So this is the constructive interface. So they meet constructively at 3 seconds. See, giving you a peak. And destructively means one, there are coming two waves having, 180-degree phase, and they mean, so at this 3.5 second, the wave just vanished, right? At this point, because they meet destructively. And here's more examples. So can you guess? So if two waves meet like this, at 6 seconds after they travel like this, what would be the? You can guess what would be the answer, resultant wave. So now the next important part is standing wave. So what is standing wave? So now let's see what's going to happen if you superpose or interfere two identical waves traveling in exactly opposite direction, right? So you will have these two equations, a cos kx minus omega t. This is the wave traveling in positive x direction, and this is the another wave, a cos kx plus omega t is the wave traveling in negative x direction. So they are traveling in opposite direction, right? The only difference here is just the plus and minus sign, right? The only difference. So now what happened? Let's see mathematically first. What happened if you combine superpose these two waves? So then again, from superposition principle, you just add them together and then do mathematics, right? And this is what you get after simplifying. This is the wave you get. This is the resultant wave function would be if you combine two waves traveling in. And you can clearly see this is not a traveling wave equation, because to have a traveling wave, the cos uh, the function wave function must be a function of both x and t together. This is just a function of k, this is just a function of omega. So this wave will not travel, right? Because why? This is the new amplitude, position dependent amplitude. This is a new amplitude, just like before. A new amplitude whose amplitude depends on just the position. This is a constant quantity, depends on position. And this is just cos omega t, and this is just a simple harmonic oscillation, right? If you have cos omega t, just the omega t factor, it just depends on time. This is a simple harmonic oscillation. It doesn't travel. This whole wave pattern doesn't travel along the x direction. So that's why this is called a standing wave. And this is the standing wave equation. So here's more graphical explanation. So the next video I will be showing you the actual standing wave in a lab, how we do a standing wave lab in a lab, and also check out the animation video. So here's the explanation, right? So here you have two identical waves traveling in opposite direction, and here's the resultant. Here's the resulting wave, right? And you can clearly see the resultant wave pattern doesn't move in x direction. So that's why it is called a standing wave. And it just vibrate. It just oscillate in y direction, like up and down, right? Oscillate in a fixed position, and that's why it is called a standing wave. And in this standing wave pattern, you can see some points do not vibrate at all. Some points just some points have zero vibration, like this point, right, this point. They are called nodes. Nodes means zero vibration, and some points have maximum vibration, maximum amplitude of vibration. They are called antinode. So these points are called antinode. Okay, the nodes and antinode, those are the important part in standing wave. So now let's calculate all possible standing wave pattern at different frequencies. So you have, let's say you have a string. This is a string fixed at both ends, and you vibrate the string with a mechanical vibrator at different frequencies. Let's see all possible harmonics, all possible different standing waves. This is the mathematics. So this is called fundamental. This is the first possible standing wave that you will see. And first possible means, since this is fixed at both ends, this end is fixed, this end is fixed, this should be the position of, no matter how you oscillate it, this should be the positions of node, because they can't vibrate. Node means, position of node means no vibration. So this is called fundamental standing wave, fundamental vibration, or first resonance. So what's the condition? What's the boundary condition for first resonance or fundamental? This length of the string has to be half the wavelength, because how much is this in terms of wavelength? Is half the wavelength, right? It's node to node distance. All right, node to node distance is node to node distance has to be half of wavelength. From here to here, half of wavelength. So if the string satisfies this condition, right, if you apply a right frequency, so it matches this, then you get the first harmonic. Now, once you find the first harmonic, then you can find all the possible harmonics. So, for example, what would be the second harmonic? Second harmonic should satisfy like this. The length has to be equal to. So, what would be the wavelength length in terms of wavelength? This is a full wavelength, right? This is a full wavelength because half wavelength, full wavelength. So if L satisfy the full wavelength, then you can get a second resonance and third resonance and so on, right? Also check out the animation video. And in short, you can say this. You can say this. These are the possible harmonics, right?
The scenario of a jump. Now, I can find any of the other all of the other harmonics are multiples of this number. So we just saw that 2 times this number was the second harmonic, or the second possibility. Well, if I go 3 times this number, I should get the third harmonic. Well, 3 times 8.5, I guess that was around 25.5. And there we go. So that's the third harmonic. How many wavelengths is this? Well, it's 1 and a half. 1 1/2 wavelengths. And it's easier to see in high speed. So check out this shot with the high-speed camera and verify for yourself that it is 1 1/2 wavelengths. So again, third harmonic, 1 1/2 wavelengths. Well, let's go to the sixth harmonic. The sixth harmonic will just be double this frequency. So we go up to 50. And there we go. That's the sixth harmonic. Beautiful. And it's 6 times the fundamental frequency, which we measured in the beginning to be 8.5 hertz.
So the speed of wave in a string depends on these two quantities. The speed of wave depends on the tension in the string and the mass per unit length of the string, which is also called linear mass density. And the formula, so I'm not deriving this formula. So the formula for the speed of wave in a string is given by square root of the tension force divided by the mu. Mu is the mass per unit length. So here's the standing wave on a string lab, that we're supposed to do in a lab, and you will see actually. I'm gonna show you a next video, the actual lab. And there are many examples of standing wave. Even microwave, your oven, microwave oven in a kitchen can actually form a standing wave from the microwave because due to the size of the dimension of this, the microwave can travel back and forth within that box, and then it can form a standing wave. And this is the real picture of infrared picture of the real standing wave formation. From the microwave. This is from the microwave. You can clearly see the hot and cold spots, right? And that's why a microwave has a turntable, right? Because otherwise, one spot will be always cold, one spot will be always hot because of the standing wave formation. And there are more links to study, resonance. And this Tacoma Bridge, collapse is also resonance. So I'm gonna do a separate video on some sample problems. So finally, on a standing wave, you can also form a standing wave on a pipe, in a pipe, like organ pipe, right? A pipe could be open at both ends, one end could be closed, and so on. It depends on the boundary condition. So here, so the first, if the pipes are open in both sides, right? This is the fundamental vibration, right? Because this has to be antinode, this has to be antinode position because they are free to vibrate, and this is the fundamental, right? and this has to be half of. So if the length of the pipe has to be half of wavelength, because antinode to antinode is half of wavelength, and lambda is this, and the first frequency is V over twice L, right? And you can go to higher harmonics. This is the second harmonic you can get, which is lambda has to L has to be, L has to be full wavelength, and then this is the third harmonic and the fourth harmonic and so on, and then this is the general formula, right? And however, if one end is closed, right, this will change the fundamental frequency. So now the boundary condition has changed. So the length has to be equal to, node to antinode distance, which is lambda over 4, and then calculate the lambda and frequency, right? So here you can clearly see, right, the difference between these open end pipes and one end closed end pipes. That will change the fundamental frequencies and resonant frequencies. And also check out the animation video.